Most people think of concrete as a very hard and dense material surrounding us in daily life, providing shelter, and making our homes safe. If we look at concrete in its freshly mixed state, it flows like porridge. It takes 2 to 3 hours to solidify from a liquid state to a solid state. If you want to mold and cast concrete, you must get it done within this 2 to 3 hours. Otherwise, a slump loss happens. If concrete arrives too late, placing of concrete would be very difficult. In such cases, we call the concrete not workable. Let's look at 2 examples. First, consider a tall wall formwork containing tons of steel bar matrix. Pouring late or unworkable concrete would not be able to fill up every corner of the wall. Therefore, honeycombs and voids would be left everywhere in the wall. Secondly, segregation could also happen because aggregates and paste separate from each other. Both of these situations would result in weakened strength, structural integrity, and durability of the concrete structure in the long run. Before molding fresh concrete into formwork, a good check on site to see if fresh concrete is workable or not is known as the workability test. The workability tests measure the consistency of fresh concrete between batch to batch, hour to hour, and truck to truck variation of concrete. 3 of the most commonly used workability tests are slump test, VB time test, and compaction factor test. First, we start with the most popular workability test, the slump test. A basic overview of the slump test is to place fresh concrete in this slump cone, which restricts its movement. Later, when we lift up the cone, concrete becomes unsupported and flows from the effect of gravity and its intrinsic frictional force. We then measure the extent of collapse to obtain the slump value. Before learning the steps, let's look at the apparatus that you will need and how to sample fresh concrete properly. For conducting a slump test, you will need a slump cone, a scoop, a compacting rod, a base plate, a shovel, a leveler, a measuring tape, and a moist cloth. A thermometer may be required if the environment is too hot or cold. All apparatus has to be cleaned prior to use. Now Jones will show you the sampling technique in the slump test. Use the scoop to take the required quantity uniformly distributed throughout the batch of concrete. Uniform is the key word here. For all these scenarios, sampling the very first or very last portion of the fresh concrete is a common mistake, yielding wrong slump values, just like what Jones is doing right now. This is because concrete at the very first portion may be more likely to locally contain a much higher water-to-cement ratio, while the very last portion may be more likely to be segregated. There are 3 steps which must be followed strictly to perform the test. The first step is preparation. The second step is molding. And the last step is measurement. Watch carefully now as Jones performs each of these steps. 1. The first step is preparation. A. Dampen the mold and base plate. B. Level the base plate with a leveler. C. Attach the mold on the horizontal base plate. D. Hold the mold firmly on the 2-foot pieces against the base plate while filling with concrete. 2. The second step is to fill the mold with fresh concrete. A. Fill the mold in 3 layers, each approximately 1/3 of the height of the mold when compacted. B. Compact each layer with 25 strokes of the tamping rod. C. Distribute the strokes over the cross-section of each layer. D. For the middle and top layers, compact each layer throughout its depth, so that the strokes just penetrate into the immediately underlying layer. E. For the top layer, heap the top layer of concrete before tamping is started. F. Add more concrete to keep an excess above the top of the mold. G. Strike off the surface of the concrete by means of a sawing and rolling motion of the compacting rod. H. Remove spilled concrete from the base plate. Three. The third step is to remove the mold and take readings. A. Remove the mold from the concrete by raising it carefully with a steady upward lift. B. Record the slump to the nearest 10 millimeters by measuring the difference between the height of the mold and that of the highest point of the slumped test specimen. The test is only valid if it yields a true slump in which concrete remains substantially intact and symmetrical. If the specimen shears in this way, this is an indication of lack of cohesion in the mix. The test data should be rejected and another sample should be taken and tested. In actual site practice, the test is carried out much faster. Watch the test again at normal pace. See if you can follow what he is doing in each of the steps. The second workability test is the VB time test. This test measures the remolding ability of fresh concrete under vibration. For conducting a VB time test, you need the same tools as for the slump test. In addition, you will also need a VB consistometer, a stopwatch, and a vibrating table at a frequency of 50 to 60 Hertz. The sampling technique of concrete in the VB time test follows that of the slump test. You have to sample the middle part of fresh concrete to avoid high water to cement ratio or segregation. Again, 3 steps must be followed strictly to perform the test. The first step is preparation. The second step is molding. And the last step is measurement. Watch carefully now as Jones performs these steps. The first step is preparation. A. Place the VB consistometer on a rigid horizontal base. Fix the container firmly to the vibrating table by wing nuts. B. Dampen the slump cone and place it in the container. C. Swing the funnel into position over the mold and lower onto the mold. D. Tighten the screw so that the mold cannot rise from the bottom of the container. The second step is molding. E. Fill the mold in 3 layers, each approximately 1/3 of the height of the mold when compacted. F. Compact each layer with 25 strokes of the tamping rod. G. Distribute the strokes over the cross-section of each layer. H. For the middle and top layers, compact each layer throughout its depth, so that the strokes just penetrate into the immediately underlying layer. I. For the top layer, heap the top layer of concrete before tamping is started. Add more concrete to keep an excess above the top of the mold. J. Strike off the surface of the concrete by a sawing and rolling motion of the compacting rod. K. Remove spilled concrete. The last step is measurement. M. Remove the mold from the concrete with a steady upward lift. N. Swing the transparent disc over the concrete. O. Loosen the screw and lower the disc until it just comes into contact with the concrete. P. Start the vibration of the table and the timer simultaneously. Observe the way the concrete is remolded through the transparent disc. Q. As soon as the cement grout comes out around the perimeter of the disc is fully in contact with the cement grout. Stop the timer and switch off the vibrating table. R. Record the time taken to the nearest second. Watch while Jones carries out the test again at normal pace. See if you can follow each step. The last workability test is the compaction factor test. For conducting a compaction factor test, you will need an apparatus with 2 conical hoppers and a cylinder mounted on a rigid frame. A vibration table and a weighing machine. Of course, you also need the same tools as in the slump test. The sampling technique of the compaction factor test follows that of the slump test and the VB time test, so we are not going to repeat that here. The first step is preparation. A. Place the compaction factor apparatus on a rigid horizontal base. B. Clean the container and moisten the inner surfaces using a moist cloth. The second step is molding. C. Fill the top hopper with non-compacted concrete. D. Open the door at the bottom of the top hopper so that concrete drops into the lower hopper. E. When all concrete falls from the top hopper, open the door at the lower hopper for concrete to flow into the bottom cylinder. F. Use a tamping rod to force sticky concrete through the hoppers. G. Strike off excessive concrete from the top of the cylinder. The last step is measurement. H. Record the mass of concrete in the cylinder. Note here the concrete is not compacted. I. Compact the same batch of concrete in the cylinder with a vibration table. Add concrete up to the top of the cylinder. After vibration, Record the mass. J. Calculate the compaction factor by dividing the mass without to the mass with compaction. This is the end of the procedures. Watch the test again. See if you can follow each step. The slump values, VB time, and compaction factors are very dependent on the lapsed time after mixing. A longer lapsed time surely yields smaller slump. Longer VB time, smaller compaction factor, because water evaporates. Therefore, the workability test must be done just after mixing finishes. Next, we will introduce some other factors that affect the workability from materials perspective. These factors are water to cement ratios, partial replacement of cement by fly ash, dosages of superplasticizer, aggregate type and grading, aggregate to cement ratio, cement fineness, temperature, humidity, etc. Here we introduce the first three factors: water to cement ratios, partial replacement of cement by fly ash, and dosages of superplasticizer. Look carefully at how these factors affect the workability. Firstly, water to cement ratios. It is obvious that the more water you add in the mix, the better workability you obtain. Secondly, the partial replacement of cement by fly ash. The spherical shape of ashes effectively disperses over and gets absorbed on cement, which makes water distribute more evenly and increases the workability. Thirdly, dosages of superplasticizer. The long molecules of superplasticizer wrap themselves around the cement particles and become negatively charged so that they repel each other. This results in deflocculation and dispersion of cement particles, and concrete gains better workability. For high dosages of superplasticizer, the slump, VB time, and compaction factor tests are not the appropriate measure anymore, since concrete spreads over. Instead, we measure slump spread and some other tests for self-compacting concretes, which will be discussed in another video. The slump, VB time, and compaction factor tests are suited for concretes of different levels of workability. For example, VB time is suitable for concrete of low but not high workability. Therefore, selection of test methods depends on the anticipated range of workability. The values of slump, VB time, and compaction factor tests are highly related to one another. For example, for concrete with high workability, you will expect a high slump, a low VB time, and a high compaction factor. So far, we have discussed the importance of the workability tests and demonstrated the detailed steps for conducting proper workability tests that yield accurate results. In general, a smaller slump value, a longer VB time, and a smaller compaction factor mean the concrete is less workable and less easily handled, and vice versa for a larger slump value, a shorter VB time, and a larger compaction factor. On-site, slump test is the simplest and the most widely used workability test, and deserves more attention compared to the VB time and compaction factor tests. Normal slump values range from 50 to 150 millimeters, and the more detailed workability descriptions of the slump values are listed here. The slump values have to be carefully controlled to cope with different on-site concreting conditions, such as whether a pump truck or tower crane is used, in situ temperature and humidity variations, and so forth. The slump, VB time, and compaction factor tests are used and standardized all over the world. There are two main advantages of the test. First, the test determines the workability and consistency of in situ concrete, which provides a scale on how easily it can be handled, compacted, and cured. Second, engineers also make use of the results of trial mix to alter the concrete mix to achieve additional concrete strength and durability. By watching this short video, we hope you've been able to understand three main points. 1. The three-step procedure and the underlying principles of the slump, VB time, and compaction factor tests for concrete. 2. The reasons for carrying out the slump, VB time, and compaction factor tests, such as inspection of consistency and workability. And 3. The three factors affecting the slump, VB time, and compaction factor values. This includes water to cement ratios, partial replacement of cement by fly ash, and dosage of superplasticizer. Next time, when you walk by a construction site and see concrete mixing trucks coming and going, we hope that you may recall the contents that you learned from this video. That's all for this video. Thanks for watching.